To solve this problem, we need to get a from the equation a equals final speed minus initial speed over time. We substitute the values given in the problem and solve for a. Then a equals negative 98.6 km per hour over 0.3 seconds, which is negative 329 km per hour second. To work out the units, we divide kilometers per hour by seconds. It's the same method used to solve a division of fractions. We can rearrange to kilometers per hour times 1 over seconds. We multiply numerators to get the final numerator and denominators to get the final denominator. So we end up with kilometers per hour second. This answer tells us that Wario's speed decreases by 329 kilometers per hour every second. Now let's convert this speed into meters per second. We use our conversion factors, one for length units and one for time units. We now have 329 km per hour times 1000 meters over 1 kilometer times 1 hour over 3600 seconds. We end up with 91.3 meters per second. We substitute this value in place of 329 km per hour second and we get negative 91.3 meters per second squared. That's another way to see Wario's acceleration. He slows down 91.3 meters per second every second it passes. At the end, Wario had a negative acceleration because of that blue shell. Let's assume Wario's brute kart has an acceleration of 13.1 meters per second squared, and it can reach a maximum speed of 98.6 kilometers per hour. How long does it take Wario to reach that speed right after the race starts? We solve a equals final speed minus initial speed over time, but this time for t. We multiply both sides of the equation by t and we get a times t equals final speed minus initial speed, and then we divide both sides by a to end up with t equals final speed minus initial speed over a. We can substitute values now, so the equation turns into t equals 98.6 km per hour divided by 13.1 meters per second squared. After solving, we get 7.53. Wait a second, something doesn't look right. What about the units? Let's calculate the units. So we had kilometers per hour divided by meters per second squared, which is the same as kilometers over hour times second squared over meter. We multiply numerators and denominators and we end up with kilometers times second squared over hour times meters. We only wanted to know how long it takes to reach that speed, but we just got units of speed times units of time divided by units of length. In a nutshell, something went wrong. But what? To understand what we're calculating, we need the right units. In this case, we needed the speed in meters per second, not in kilometers per hour. Why, you ask? The acceleration is in meters per second squared. Different length units, different time units, everything is mixed together. The equation we used is correct. The only problem is that we mixed incompatible units. Don't worry, we can fix it by multiplying that 7.53 kilometers times second squared over hour meters by these conversion factors, 1000 meters over 1 kilometer and 1 hour over 3600 seconds. We end up with 2.09 and we cancel out kilometer, meter, hour and second to get only seconds. There it is. It took Wario 2.09 seconds to reach his maximum speed of 98.6 km per hour after the race started. You can also convert the units of speed from the beginning. Converting from the beginning or using conversion factors at the end gives the same result. It doesn't matter as long as you get the right units. Remember to always choose the most convenient units. There are 4 variables in the acceleration equation: acceleration, final speed, initial speed, and time. We know how to get acceleration and time. Let's discover how to get speed. Wario is driving at 98.6 km per hour when he gets hit by a red shell. The red shell gives Wario a negative acceleration of 18.6 meters per second squared during 1.4 seconds. What is his final speed? We isolate the variable Vf from the equation A equals Vf minus Vi over t. We multiply both sides by t to get At equals Vf minus Vi and add Vi on both sides to end up with Vf equals Vi plus At. Before we substitute, let's convert 98.6 km per hour into meters per second. We need our conversion factors to finally have 27.4 meters per second. Now we substitute to get final speed equals 27.4 meters per second plus negative 18.6 meters per second squared times 1.4 seconds. Don't forget that minus sign. We solve final speed equals 27.4 meters per second minus 26.0 meters per second to finally get final speed equals 1.36 meters per second. Wario gets hit again, but now by a green shell. That shell causes him to slow down by a negative acceleration of 17.7 meters per second squared. His speed after 1.2 seconds is 3.75 meters per second. What was his initial speed right before the shell hit him? We start from the same equation, A equals Vf minus Vi over t. We multiply by t on both sides and then subtract Vf also on both sides to get At minus Vf equals negative Vi. We multiply both sides by negative 1 so that the initial speed is positive, and we end up with Vi equals Vf minus At. Now we substitute initial speed equals 3.75 meters per second minus 17.7 meters per second squared times 1.2 seconds to get Vi equals 3.75 meters per second plus 21.2 meters per second, which gives us initial speed equals 24.9 meters per second. Now it's time for Wario to get into the baby pack circuit. He completed the first lap without using any item, so his speed was constant. We calculated dividing the track length by the time taken, and we called that the average speed. Then he completed the second lap using a mushroom, but then he got hit by a blue shell. In this case, it's clear that he had an acceleration when he used that mushroom and a deceleration when he got hit by the blue shell. There was a change in speed. He sped up and then slowed down during the lap, so he finished that second lap with the same time as the first one. His speed in the second lap is the same as the speed in the first lap because it's the same distance traveled and the same amount of time. As you can see, in both scenarios, the average speed is the same. Does that mean average speed and acceleration are the same? Not really. Average speed summarizes an object's motion as if it had moved at one constant speed during the entire trip without showing what happened at every moment. But mathematically, it's the same description. no matter if the object changes its speed during the trip. It can be described by its average speed. This is the end of the video. Here's a problem for you. If you enjoyed this video and learned something new, don't forget to like and subscribe. See you next time.